PhD student, major in atmospheric science at SOMAS, and I'm working with Christopher Wolf here and Dr. Kevin Reed. Dr. Christopher Wolf is a physical oceanographer, and he's interested in the ocean dynamics like Gulf Stream. Then Dr. Kevin Reed is a climate scientist. He is interested in the climate extremes like tropical cyclones. So we are trying to understand the climate and tropical cyclones through simplified imaginary Earth. I'm so glad to have this opportunity to share our research in front of the audience from different backgrounds. And thank you, IACS, for providing this opportunity. I will divide my presentation into several sections: introductions of the climate and tropical cyclones, and narrow down to our research motivations, and introduce our model configurations and show some results of our model output, then go to the conclusion and our future plan. So why do we care about tropical cyclones? First of all, from the perspective of societies, tropical cyclones bring the human beings a series of natural hazards like storm surge, the inland flooding from heavy rains, destructive winds, and high sea state. These natural hazards damage people's properties and threaten their lives. Well, driven by the society's need, the climate scientists, the tropical cyclones also bring a series of hard questions to the climate scientists. For example, how tropical cyclones form and their movement, what the magnitude of their movement, why they suddenly take turns in the middle of the oceans, and their interpretations, why it suddenly grow from category 4 to 5 in just a sudden night. For example, if we look in details for some conditions of tropical cyclone formations, for example, we look back to the data over 100 years we have every tropical cyclones, we will find that the tropical cyclones always usually form at a very warm sea surface. So like the figures on the right, above a very warm oceans, the air is also warm and moist. And the oceans provided lots of heat and waters into the air, and then need perturbations for convergence of the air, so the air could have some momentum to go up. And then during their rise, the water vapor will condense to the droplets and form the cloud. And it's as long as the oceans provide enough water and heat, and this process will go, and the storm cloud will grow and grow. However, for the figure 2, in this development, the wind shear cannot be very strong. If the upper air flow like this and the lower layer air flow like this will kill this upwelling process. And also the tropical cyclones need to form several degrees apart from the equators, so that the whole storm could rotate. Once the large cluster of the storm clouds starting to rotate, tropical cyclones is formed. So it's obvious that the formation of tropical cyclones is very delicate, requires lots of conditions. So it's obvious that once the environment variable will change in the future, so it will definitely influence on the tropical cyclone formation. For example, for this topic, like the research from Chad et al. 2022 pointed out that based on their analysis over the past 100 years, they find that the weakening of the tropical circulations, like Hartley and Walker circulations. Hartley circulation is meridional overturning, rising on the equators and going down on the subtropical area. And Walker circulation is zonal overturning circulations. Well, for examples on the Pacific, Y is in the western tropic Pacific and going down on the eastern Pacific. And these two tropical circulations, once it's weakened, will bring a reduction of the ascending motion and the greater evaporation and reduce the net buoyancy of the cloud. So all these conditions are unfavorable to the TC formation. However, this is not the only answer to this question. A lot of research give a series of opposite answers. So this topic is under debate right now. So this leads to our first objective is the first objective that is we want to investigate the impact of zonal symmetric. That means without the Walker circulations, the zonal overturning. There's my. Oh.
You should be able to click out that.
Yeah.
There's a box up there that you might want to refer to the closed captioning.
The zonal symmetric climate is without the Walker circulations, and the zonal asymmetric climate means the climate is with the Walker circulations. So we wanted to investigate what the impact of this situation of these two cases on the formation of tropical cyclones. However, the tropical cyclones still welcome. However, the tropical cyclones are not a passive player in the climate. It means it will have the feedback to the mean climate. For example, the ocean provided heat to the tropical cyclone, and at the same time, the tropical cyclones generate a high wind applied to the sea surface. So it's providing mechanical energy to the oceans. So that's why we usually see a cold sea surface temperatures weak along the tropical cyclone track. That means if we look at the temperature vertical profiles of the ocean temperatures, that before the storm, a very warm layer sitting above the cold waters, and after the storm, the warm waters on above temperature decrease, and the cold waters temperature getting warmer. So that was stir. That means the tropical cyclone stir the whole columns of the water, and actually the net effect is injected heat into the deeper oceans. That means tropical cyclones actually help use their work to help the climate system to recycle some heat, and the climate system use this recycled heat to redistribute it among globally. So where this heat goes and how the impact on our global climate is another question we want to answer. Also, the tropical cyclone also included a lot of irreversible process, like the forming of the droplets, mixing, and falling down the raindrop, and the fractions. And these processes are very important to the future and to help us to diagnose our future climate. So our general objective is to want to investigate the tropical cyclone and climate interaction, how the long-term climate impact on tropical cyclones, and how the tropical cyclone feedback on the large-scale climate. Well, for our human beings, we started to carefully record the tropical cyclones just from several decades ago. So we need actually for climate research, we need longer time series data. In this situation, climate models become our useful tool. Well, speaking of climate models, people are usually thinking about we're saying about the very advanced climate models, the comprehensive climate models. It includes lots of components in the Earth systems like atmosphere, ocean, and land, and cryosphere. Like the dynamic, it includes a process like that, the circulation in the atmosphere, and the temperature changes in the oceans, and how the land cover and land use in the land model, and the sea ice and land ice comes and goes in the ice model. And we used this advanced climate model first to simulate the climate in the past, current, and future. For example, the climate scientists will cooperate in the framework of Intergovernmental Panel on Climate Change (IPCC). So the climate scientists from different institutions and different countries, they run their own climate models under the same standard and putting their output, their result together and analyze it in the same way and to evaluate our future climate. And every 5 to 6 years, they will release an annual report. It includes the consensus among the whole climate community and how much confidence we have on our results. So lots of it will inform the policymakers and to setting, for example, setting our climate goals on each countries and guided the negotiation with each other. And also the advanced climate models is a virtual lab for the scientists to do experiments to investigate the mechanisms on in the climate. For our human being cannot use our own force to change the circulations of the real Earth, right? And we cannot say vanish this, making this circulation vanish, but we can do it on the computer. And another use of climate model is the climate data simulations that were provided a best guess based on the climate model output and our observation to give the most accurate estimation of the climate state, the past and the current. And the climate model is not a black box. It's actually just criticize the Navier-Stokes equations of the stratified fluid on the rotating coordinate. On like in the figure on the left, it divided to a little grid point, and we calculate the number on each box. And also a set of parameterizations computes the subgrid scale physical process, like very small scale process, like turbulence, eddies, and small cumulants. And for examples, these equations are the governing equations on MOM6, is an ocean model. Generally speaking, the total derivative terms is on the left, and the forcing term is on the right-hand side. So the comprehensive climate model is very fancy and complicated. It's a good tool to estimate our real world as far as we can, but it's too complex. It's the complexity and the high expense limit our abilities on understandings. So we want a simplified and cheaper tool to fill this gap. For example, nature provided us a hierarchy of biology systems of increasing complexities. For example, in the medical science or biology, people started to understand the organized, understand the mechanisms in organisms, from the bacterial, fruit fly, mouse, then to the human. And then what we learn from the very simpler organisms can rely on the complex organism. And the same way as our climate model, we need a very simple models to advance our understanding. So we choose the community Earth System model, CSM, as our starting point. So why we choose CSM? First is the open source climate model. It's maintained and support and evolved by the community. So every user could contribute on it, and every user could see their discussions and revisions on the code, and everyone could download it. And also, these models are strongly tested and maintained. And the simplified climate model we use is aquaplanet. The aquaplanet is a water-covered climate model. There is no land on it. Overall, the global is the ocean, and the physics is almost identical to the comprehensive climate models. So the major simplification is the lower boundary condition. There is a rich history for aquaplanet's development. In 2021, people released a series of settings, standard settings for the aquaplanet. And in CSM version 2, it released a supported version for it's very user-friendly version for people, scientists to use in the aquaplanet, but it's only included the atmosphere. It's with a fixed ocean, so the ocean doesn't change with time. In 2021, Wu, our previous lab members, developed a coupled climate models. It includes the dynamical ocean, so the ocean and atmosphere will interact and together and evolve with time. And then when our current work is first increase the ocean model resolution from 2 degrees to 0.66 degree. This 0.66 degree is comparable to the comprehensive climate models now in the oceans. And then we change the bottom topography from sinusoidal to the flat bottoms to simplify the bottom friction. Then The details for our model configurations is showing like in the figure on the left. So the aqua again is the water cover planet, and the ridge we added a very narrow 1 degree points wild continent from the North Pole to the South Pole. And in our coupled aqua planets, we include the atmosphere, ocean, sea ice, and land, and they communicated with each other every time step through the coupler. And we run our simulations on the NCAR one, the supercomputer, science supercomputer in NCAR Wyoming Supercomputer Center. For Cheyenne, it's Intel Broadwell processors and have 4,000 nodes, 36 core per node, but it will retire on the end of this year. There's new clusters on Wyoming supercomputer centers at the ratios, and will have the AMD Milan processors and 64 cores per node, is about 3.5 times larger than the Cheyenne. And here are some our simulation performance on Cheyenne. We run it on 20 nodes, that is 720 cores, and we spend about 750 core hours per simulated years, and every 24 hours, a model could provide about 24 years output. And comparing to the most advanced and the latest CESM comprehensive climate models, and they run on 2,000 cores and spend about 6,000 core hours per year, and run much more slowly. Well, it's more expensive and more slowly for experiments. And for the estimations of our total model cost is about 10 million core hours in total, including the current experiments and the experiments we designed for the future. And another fact for the couple model is the load balance. That means you need to allocate it appropriate number of resource on each component of your couple models. For example, in the figure on the left, the y-axis is the time consuming by each component finish their job, and the x-axis is the MPI number of MPI ranks. If you in this case, is obviously you give the ocean models a much more MPI ranks than it needs, and so the ocean models finish their job very fast. And however, the atmosphere and land models is still running. So the black means the ocean model is in idle and waiting for the output from the atmosphere and land. So that's waste a lot of time. If we balance our layout, we have fewer MPI ranks on ocean and more on atmospheres, then maybe they will shorten the waiting times. And we also work with IACS as a team to utilize the computation resources on our campus on IACS. We port in the MOM6, our ocean component models on Okami and Seawolf. We test the performance of MOM6 using different compilers, and we find that on the Okami, Fujitsu compilers give us the best performance, and we also test the performance of MOM6 on different nodes on Seawolf, Milan nodes, super-rapid nodes, and the results is that the super-rapid nodes with GCC compilers is most suitable for Month 6. So the benchmarking work is still undergo now. And here I'm going to show the result of our climate simulations. So again, why do we need to choose a climate state? If we look back to our objectives, we wanted to investigate the impact of zonal symmetric and asymmetric climate on the environmental condition favorable to TC formations. And if we look at this is the time average sea surface temperatures on the map. The y-axis is the latitude, the x-axis is the longitude. For the aqua planet, all the sea surface temperature are zonal symmetric. And for the ridge, the sea surface temperatures have warm centers at the east and center of the basins and cold tongue on the east side of the oceans. So it's zonal asymmetric. That will lead to upwelling atmosphere rising on the east side and atmosphere and descending on the east side. Yeah. So that's why we need the two configurations, and also it's generated naturally by the physics. It's not we artificially added some forcing. Now it's an exciting time for us to push the buttons to submit the job, and the simulation is starting running. And after a few days, you'll find that if you plot the global mean sea surface temperatures as a time series, you will find for aqua the sea surface temperatures drop dramatically from the initial conditions and gradually and slowly seems like saturated on some kind of values, and for the ridge configurations, also the sea surface temperature is still evolving. So why that happens? That is because if we consider the climate as a heat engine, for example, the panel on the right for Figure A, this is the ideal Carnot engine. We put the heat into the engines and the engine do some work ideally and emit the resting heat outside. And for the figure here is like the engine on our car. It has some irreversible process to cause some extra work. But for the climate, it's totally different. It's a little bit different. We also we absorb the heat from the solar radiations, and this is the Q in, and we also have the long wave emissions back to the surface, back to the space. So that is Q out, and the heat difference drive the air and the oceans moves. That produces some useful work, but there is no external bodies for the climate. So the work will apply on the climate itself, and also with some irreversible process. The basic point is here is that we want the Q in equals to Q out. That is true for the real climate. But in our simulations, it's still not. So that we still not reach the climate equilibrium. If we plot the Q in minus Q out in 1 meter squared, we will find for the aqua planet, is the number is the positive, so it's still absorbing heat from the space. And for the ridge, it also absorbing heat right now. It's not reaching the static state. If we calculate, if we integral the Q in minus Q out all over the world, the x-axis is the latitude and the y-axis is the total heat energies absorbed in the tropical area and emitted in the higher latitude. We will find that there are several p watts imbalance for globally. That's a huge number. And then if we look at the sea surface pressure, we will find that it's gonna reach a steady state, but still not. And if you look at the temperature inside the oceans, we will find the ocean is the temperature in the ocean is largely increased right now. And then this figure shows the zonal symmetric and zonal asymmetric of alkaline ridge configurations. For the y-axis here is the depth, the ocean depth from 0 meters to 500 meters depth, and the x-axis is the longitude. We can see inside of the basin, ocean basins, the aqua planets have a very thin layer of the warm water and very thick layer of cold waters sitting beneath it. And for the ridge, the situation is totally different. Warm water, large volumes of warm water stack on over the center and the western basins, and there is cold waters extended near the surface and to the east side of the basin. Then, if you look at the precipitation, the freshwater flux and the relation between the freshwater flux and the the ocean salinities, we will find that it's corresponding to each other. We have a rain belt. The panel on top, these two are identical, and the y-axis is the precipitations minus evaporation. That is means the freshwater flux, and the x-axis is the latitude. We have the two large ring belts sitting in near the equators, so that corresponding to surface minimums of the ocean salinity, and a large evaporation. A lot of fresh water leaving the ocean, corresponding to the salinity maximum on the surface ocean surface. And on the higher latitude, the rain belt on higher latitude produce lots of fresh waters into the oceans, and the fresh waters all the way sinking into a very deep, deep layer. For the aqua planet, for the ridge planets, the high salinity layer is going shallower, but it's also corresponding to the freshwater flux and the ocean salinity. And if we look from the view of space, we can see the horizontal circulations of the oceans. For the aquaplanet, the circulations is just go one direction, driven by wind, because there is no land, so the wind accelerated, go round and round, and also the high wind driven the oceans go one direction in very high velocities. And for the ridge, the contours are the string functions. It's indicate the velocity, the directions of the velocities, and we can see the solid is positive clockwise. So like in this gyre, the circulations go to the east and then turn back, go westward and go northward. It's very similar to the real world ocean circulations. And we have the western boundary, a very energetic and rapid jet flow at the western of the oceans like Gulf Stream or Kuril. And if we look at the zonal current, the y-axis is the depth and the x-axis is the latitude. And we dive into the ocean to see the directions of the zonal currents. We'll see that the aquas on the equator near in the tropical area, the flow is flow to the east, the same directions with the wind, and the velocity damps when we go deeper, but it's extended to a very deep layer. And on the high latitudes, the oceans go in another direction to the from the west to the east. And for the ridge, it's more realistic comparing to the real climate. You notice that we have the equatorial undercurrent under the thermocline. It has the opposite directions of flow comparing to the surface flow. It's real in our climate. It also shows in the ridge simulation. And then we investigate the meridional overturning circulation. The y-axis is the depth and the x-axis is the latitude. The contours are the streamline, the spring function, the streamline of the velocities, and the solid is the positive clockwise. So the water sinking here and rising near the equator. Well, it has a very deep subtropical sails. However, for the simulation is the string function should align with the temperature distributions. Well, for our simulation right now, it's not. Maybe because it's still in the adjustment, in the climate adjustment right now. We are expected to see the string function align with the temperature contours once our simulation reach the climate equilibrium. And for the ridge, we can see the overturning goes to a very shallow layer. In this case, north hemisphere goes sinking here, but it just can reach less than 1,000 meters and going back, upwelling to the equator. Here is our conclusions right now. In summary, our aqua and ridge have a simplified boundary condition. comparing to the complex climate models. And our spin-up simulation is still continue until we get the climate equilibrium. And the aqua has the zonal symmetric climate, and the ridge has zonal asymmetric climate. And the aqua has the equatorial sea surface cold belt, and the ridge has the western warm pole and eastern cold top, more realistic comparing to the real world. And the ridge has more Earth-like feature than the aqua. And our future work, there are lots of work need to do. We are in this first step right now. So we wanted to analyze the environmental conduciveness of the tropical cyclone formation based on the two mean climate. And then we need to run a higher atmosphere model, higher atmosphere's resolution of the atmosphere model to resolve the tropical cyclone. For now, our atmosphere model is 1 degree, but it's not enough to see a tropical cyclone very clear in our simulation. So we want to increase the resolution. That means we need to increase the computational cost. And then we want to investigate the tropical cyclone trend in the climate and the warming climate, and evaluate their feedback climate. And that's all the information today. And I'm welcome for the question.
Okay.
By range, you mean like from north to south, right? The range is a single range of the
Right.
Was the asymmetry in the ridge model caused because of the rotation of the Earth, or what caused that?
It's because of we add land in the middle of the oceans. So the pressure, if we calculate the pressure over the latitude circle, is for the aqua, the starting point is the ending point. So you get zero pressure gradient. And if you put a land at the inside, so the values at the starting point is different from the value in the other side. So it's more realistic to the real climate, and the appearance of the pressure gradients will drive these features here.
Okay, so I'm just curious, like, if you have that ridge in the middle, what differentiates one side of the ridge from the other? They're just like the direction.
You mean the circulation?
I guess so.
It is the it's the total different. The circulation first, it will drive it will derive the wet boundary currents, very like the Gulf Stream, So on this side of the on the east side of the ridge, and on the other side is where there is a very slow eastern boundary current. Therefore, for the aqua, the currents were driven by the wind ozonally direction.
Okay.
There is no meridional transport in the aqua channel.
I think the answer to your first question about the rotation is kind of right, because the reason why the east and the west side of the ridge are different is due to rotation. If you spun the earth the other way, it would flip.
Okay, that's what I was thinking. Yeah, thank you.
I'm from marine science student. I'm curious to know how do we know the simulation model match with the real environmental data, or what technique and method we can do?
Okay. It's important for our result to inform the real climate But for the idealized model simulations, our aim is not to simulate the real world. Although our simulation is far more apart from the real world, but laboratories for us to do experiments in very ideal conditions. So we wanted to investigate mechanism inside of the idealized model, but it's to be honest, our result is far from the real world, but it's good for us for advance our understanding.